class. Today in this lecture, we're going to cover the section 1.6, linear inequalities in one variable. And these are the topics we're going to cover. So find the solution of linear inequalities in one variable. Use properties of inequalities to write equivalent inequalities. Solve linear inequalities in one variable. Solve absolute value inequalities. Use linear inequalities to model and solve real-life problems. So firstly, take a look at the definition of inequality. So an inequality is in the variable x is solved by finding all the values of x for which the inequality is true. So inequality definition looks just like the definition of an equation. So the solution of the equation is for all the values of x for which the statement is true. In this case, it's the similar, but in case of equation, we have the inequality. So the solution of the inequality will be all the values of x for which the inequality is true. And then those solutions will satisfy the inequality, and the set of all real numbers that are the solutions of the inequality is called the solution set of the inequality. And if you set all the points on the real number line, that will represent the set of the graph of the inequality. Graphs of many types of inequalities consist of interval on the real number line. So let's take a look at some examples over here. So over here we have three examples, as you can see, and we're going to see which one of these intervals is bounded or unbounded. And we're going to represent the interval with an inequality and sketch its graph. So the first one is -3 and 5. The second one is open parenthesis 4 to infinity. Third one is open parenthesis negative infinity to closed parenthesis at 2. So we're going to take a very close look at the parenthesis over here. So what does the closed and open parenthesis means? So whenever you see an open parenthesis, that means our solution set over here does not include the endpoint -3. And closed parenthesis means it will include the endpoint in our solution set. So that means like this interval consists of all the numbers from -3 excluding -3. So it will be all the way up until -2.9999999. So it will go really close to -3, but not exactly -3. And it will take all the numbers that are just greater than -3 to all the numbers, including number 5. So this is our range of the values of the x. And when you write it in an inequality form, it will look like this. So -3 is less than x, which is less than or equals to 5. So a parenthesis will result in a less than sign, and a second a square bracket results a smaller or equals sign. So this is something that you have to pay attention to. And the second example is the interval 4 to positive infinity. So again, I forgot to mention something about the bounded or unbounded. So we say that a interval is bounded if it has a lower bound and an upper bound. So if you can see at this example over here, it's bounded below by -3 and it's upper bounded by 5. So in this case, we have a bounded interval. And on the second one, we have a lower bound, which is 4, but on the upper bound, it's not bounded, right? It goes to positive infinity. So in this case, we say this interval is unbounded, and it corresponds to the inequality 4 is less or equals to x is less or equal to positive infinity. And the third example we have here is again an example of an unbounded interval, because even though it's bounded, it has an upper bound, it doesn't have a lower bound. So in this case, this interval is unbounded and corresponds to the inequality negative infinity less or equals x less or equals positive 2. So this solution set, or this inequality, takes all the value that less or equals to 2, positive 2. Now let's take a look at some properties of inequalities. So the procedures of solving linear inequalities in one variables are much like those of solving linear equations. So basically, whenever we solved an equation, we followed some properties or procedures. So inequalities, solving inequalities, we will follow almost the same kind of rule, but there will be some exceptions, and we're going to go through that over here. So first of all, we isolate the variable using the properties of inequalities. Two inequalities that have the same solution set are equivalent. So let's see the properties again. Over here, A, B, C, and D, they are all real numbers. And the first property is transitive property. That means if you take two inequalities, so A is less than B and B is less than C. So if you have two inequalities and they share the same variables, right? So over here they have the same variables B. So in that case, you can take these two inequality and make it into a one inequality. So you can assume that A is less than C. You can deduct that A is less than C from these two inequalities. And then you can add two inequalities. So if you have A is less than B and C is less than D, then you can add A and C, and that will still be less than B plus D. The third property is the addition of a constant. So if you have an inequality, you can add a constant on both sides of the equation. So you can add the constant C on both sides, and it will still hold the inequality. So that you can see we still have A plus C is less than B plus C. Now the last property is multiplication by constant. So if you are multiplying by constant and the constant is greater than 0, then your inequality will be the same. So AC is less than BC. However, if you have a constant that is less than 0, then your inequality changes the side. So if you started with A is less than B, after the multiplication, the inequality will change and it will turn into a greater than. So A is less than B was your before, and after multiplying with a number that is less than 0, so that would be a negative number, your inequality will reverse the symbol. So in this case, you had less than, and now you're going to have a greater than sign. And all these properties are also true if you replace the less than by less or equal, and greater than by greater than or equal sign. So all these properties holds if you add a equal sign to them. So there's that. So now let's see how can we solve a linear inequality in one variable. So take a look at this linear inequality. So the simplest type of inequality is a linear inequality, and in one variable. So this is an example of that. So we have one variable which is x, and it's a linear inequality. Now let's look at the steps of solving a linear inequality. So we start with writing the inequality first. We are writing the original inequality, and next our goal is to isolate the x, right? You can see we have x on the left hand side and the right hand side. So our goal is to bring all the x's together. So to do that, we are going to subtract 3x from both sides. If you do that, you have 5x minus 3x on this side, which will give you 2x. And then you have negative 7 over here. And on this side, the 3x will vanish, and you have just 9 over here. Now you have 2x is greater than 16. Why? Because we added 7 on both sides, because we want to isolate this x over here. So we added 7 on both sides. So when you do that, this 7 will vanish, and on this side you'll have 16. And now again, since we just want the x on this side, we're going to divide both sides with 2. And if you do that, you have x is greater than 8. So now our solution set for this inequality is all the real numbers that are greater than 8. Now, how can we write it in an interval notation? So this is the inequality notation, right? And how can we write it in a solution set interval notation? So that means our solution is all the real numbers greater than 8. So the number 8 and all the numbers greater than 8, that would be infinity. So from 8 to infinity, that's our interval. And since we don't have an equal sign, so since it's not a greater than or equal sign, it's going to be a open parenthesis. And again, this is an example of an unbounded interval because your upper bound is infinity, so it's not bounded on the upper hand. And here is a graph of the solution set. So if you draw a number line, you're gonna mark 8 and everything beyond that point. So 8 to infinity. And again, since we have a parenthesis at 8, that means 8 is not a part of the solution set. Sometimes it is possible to write two inequalities as a double inequality. So if you have two inequalities like this, you can combine as a double inequality. So if you have like 5x minus 2 is greater than or equal to negative 4, and 5x minus 2 is smaller than 7, you can combine these two, and then you have negative 4 less or equals 5x minus 2 is less than 7. So this is called a double inequality. The two inequalities can be solved together. Now let's see how can I do that. The rules we're going to follow is going to be the same as the like a single inequality, but we just have to be extra careful because we have a double inequality, right? So again, we're going to start with writing the original inequality, which is negative 3 less than or equals 6x minus 1 is less than 3. And our goal is to isolate the x always. To solve the x, we are going to isolate the x. So how can we isolate the x over here? So we can add 1 on both sides. So if you do add 1 on both sides, you have negative 3 plus 1 is less than or equals 6x minus 1 plus 1 is less than 3 plus 1. Or negative 2 is less than or equals 6x is less than 4. And then we're going to isolate the x, so we're going to divide the whole inequality with 6. Once you do that, you have negative 2 over 6 is less than or equals 6x over 6 is less than 4 over 6. Be very careful with the inequalities and keep them consistent throughout the problems. So we had the first inequality, which is less than or equal, and the second inequality is just less than. So keep consistent throughout the problem. And then once you simplify, you have negative 1/3 is less than or equal x is less than 2/3. So that's our solution. So what does it mean? It means our solution is all the real numbers that are greater or equals to negative 1/3 and are less than 2/3. So that's what it says here. And if we want to put an interval notation, we are going to write negative 1/3 and 2/3. And see, we have a closed parenthesis over here and open parenthesis over here. So that means our solution set will include the number negative 1/3, but not 2/3. So that's what the solution set graph look like. So Okay, now let's take a look at the absolute value inequality. So what does it mean, absolute value inequality? So we have all seen the absolute values, right? So when you have these like two bars and inside you have a value, we say like this is the absolute value. So what does it mean to be absolute value? So suppose you have x is your variable and or an algebraic expression. It doesn't have to be an x, it can be an expression. So it can be like ax plus c, 5x minus b, so anything like that. And a is your real numbers. And we are taking the real number and we are going to assume that a is greater than a. This part is really important. So your absolute value has to be greater than a number that is greater to 0. The solution of the absolute values of x is lesser than a for all the values of x that's lie between negative a and positive a. That is, the absolute value of x is less than a if and only if it follows this criteria, which is negative a is less than x and is less than a. So this is the definition of the absolute value. And this is for the less than sign. What happens if you have the greater than sign? So the absolute value of something that is greater than a. So in that case, this is true if and only if x is less than negative a or x is greater than a. And these rules are also valid if you replace a negative with, less than with less than or equal and greater than with greater than or equal sign. So now we have the absolute value of x minus 5 is less than 2 and we want to solve it. So let's look at the definition again. So we have an absolute value or of the expression x minus 5 and this is less than 2. So if you compare these two, we know that it follows this one, right? So we have an expression that is less than a real number a. So we're going to use this definition over here. So negative a is less than x is less than a. So that's what we have over here. So it's going to be smaller than the negative 2 and, bigger than negative 2 and smaller than positive 2. And you have x minus 5 in the middle. So whatever you have inside the absolute value, that's going to be your middle value right here. And to solve this inequality, we need to isolate the x. So to do that, we add 5 on all the sides of the inequality. So if you do that, you have negative 2 plus 5 is less than x minus 5 plus 5 minus negative 2 plus 5. And if you solve it, you have 3 is less than x is less than 7. So that means the solution set is all the real number greater than 3 and smaller than 7. And the interval notation would look like this. So 3, 7 closed by the open parentheses. So let's see, how can we solve how can we graph the solution set? So to graph the solution set below, this is how we do it. So again, our solution was 3 to 7, right? So this is our solution set. But if you look at the absolute value, so what you do is you go 2 units less and 2 units more than the number 5. So you go to like 5 and then you go 2 units less and 2 units more. So this is going to be your solution set. Okay, let's see another example. So x plus 3, the absolute value of x plus 3 is greater than or equals to 7. So when you have a greater greater or equals to u, we're going to use this definition here. So we're going to have two different inequalities. So x is less than negative a and x is greater than positive a. So again, that's what we did. So we have the absolute value of x plus 3 is greater than or equal 7. So x plus 3 is going to be less than or equal negative 7. And then x plus 3 is greater than or equals to 7. Again, we're just following the definition of inequalities. So if your absolute value is greater than or equals to a real number, this is what we follow. And we're gonna solve these two inequalities separately. These are two separate inequalities. Don't confuse them as like one line. It's like two different problems. So take a look at the left hand side for now. So you have x plus 3 is less than or equal negative 7. And now we want to isolate the x, so we subtract 3 from both sides. So you have x plus 3 minus 3, and then negative 7 minus 3. So you have x is less than or equal negative 10. And over here you have x plus 3 minus 3 is greater than or equal 7 minus 3. And now you have these three canceled each other, plus 3 and negative 3, and on this side you have 4. So x is less than or equal negative 10, and x is greater than or equal 4. So these are our two inequalities. So our solution set is all the numbers that are less than or equals to negative 10 and greater than or equals to 4. The interval notation of the solution set is negative infinity to negative 10 union 4 to positive infinity. So whenever you have two different solutions that are not connected on the number line, we include them using a union sign. So this means the solution set is this interval and this interval. So union basically translates as and. So again, if you take a look at the our original inequality, you had x plus 3 is greater than or equals to 7. So x plus 3 would translate to x equals minus 3. So we go to minus 3 and we go 7 units on the right and 7 units on the left. So this is your solution set. So again, it's negative 10 and 4. So this is your endpoints, negative 2 and 4. And our solution set is all the real numbers except this. So negative 10 to negative infinity and positive 4 to positive infinity. So that's what our solution is. Now let's take a look at an application problem. So you have two different car sharing plans. Plan A has a membership fee of $12 per month plus $9.25 per hour. Plan B doesn't have any membership fee and charges $10.75 per hour. How many hours the car must be used in 1 month for Plan B to cost more than Plan A? So our variable model would look like this. So we want to find out when the monthly cost for Plan B would be greater than monthly cost for Plan A. So now let's label the problem. So let's suppose the hours used in 1 month is H, and the monthly cost for Plan A is hourly $9.25. So 9.25 times H plus one-time fee of 12. And monthly cost for Plan B is 10.75 per hour, so 10.75 times H. And we want to find when the monthly cost for B is greater than monthly cost of A. So that means 10.75 H is greater than 9.25 H plus 12. So this is our inequality. And once we have our inequality, we know how to solve it, right? So we are going to isolate the H. So we're going to subtract both sides with 9.25. If you do that, you have 1.5 H on left-hand side. And on right-hand side, you have 12. and we can divide both sides with 1.5. If you do that, you have 8 on the right hand side. So h is greater than 8. So what does it mean? It means Plan B costs more when the car is used for more than 8 hours in 1 month. So this is what the table would look like. So for 4 hours, this is what Plan A cost, and this is what Plan B cost. For 5 hours, this is what the cost. For 6 hours, for 7 hours, and this is what for 8 hours. So as you can see, initially the Plan A was costing more and Plan B was costing less, but these values are catching up, and once it's 8 hours, they're the same, and once it's 9 hours, Plan B costs more than Plan A. So this is just like a compilation of all different solutions. So that's it for this class. I have uploaded this slideshow already on Canvas as labeled as 1.6. And if you have any questions, we're gonna talk more in class on Monday. And again, I apologize for missing the class today, and I hope to see you all on Monday.